The next speaker. Thank you. Okay, the next speaker is Marta Mazzocco, whom you can see, in Birmingham, and her title is Isomonodromic Deformations, Confluence, Reduction, and Quantization.
All right, thank you very much. And I can't see the audience, but I hope there are a few people there in Bath enjoying the sunshine and the company. Sorry, I couldn't come there physically. Well, I could, but I just don't trust it yet. So I'm a little bit of a chicken on this. So anyway, so I will discuss this. It's a little bit off topic, I think, at least with respect to the other two talks of today. But it's recent work in collaboration with Ilya Gayur and Volodya Dubtsov. And maybe what I'm going to talk about, as I said, it's off topic, but it actually fits a wider research program on which I'm working. And so maybe in that respect, we may think it's in the topic of today's meeting. So the aim for today is to present some confluent version of KZ. KZ is a system of linear differential equations which arises in theoretical physics as the system of correlation of equations satisfied by correlation functions in conformal field theory. Having said this, we can completely forget about that. It is very important, though, in representation theory, because they arise as the equations satisfied by certain module homomorphisms for affine Lie algebras. So they have their own importance in mathematics and are related to many algebraic constructions, and including the theory of R matrices and, as I said, the representation theory of quantum algebras and so on. So, as I said, this fits into a bit of a wider research program. In fact, the idea is that for the standard, I will explain what standard KZ is and what confluent is. But for the standard KZ, there is a theorem of Kohn and Greenfeld that says the monodromy of this equation is actually expressed by certain action of the braid group, quantum action of the braid group. And so for me, the motivation is that, in fact, I did other work previously to study such quantum actions of braid groups and found relations with quantum cluster algebra. So it would be very nice to link between kind of this confluent KZ and quantum cluster algebra. And also there is a link with mirror symmetry. This is a little bit more difficult to explain without writing formulae, but essentially you could say that such actions, braid group actions, are acting on objects which in nice cases are local Abbe-Yaus, for which the Gross-Seibert program works wonderfully. And in fact, the fact that we have this quantum algebra, cluster algebra appearing is not a coincidence. So for this reason, I'm interested in such equations. So the start of the work is an observation, in fact, by Reshetikin in the early 90s, in which he said that such KZ equations, at least for the Lie algebra GLM, and in fact the Katz-Moody extension of it, is the quantization of certain equations that I've come to love and study for many years, which are isomonodromic deformation equations of logarithmic connections on a principal GLM bundle on the sphere with a simple poles. So the idea of what I'm going to discuss today will be, so what I'm going to do today is going to study such object and in fact, try to manipulate this object in such a way that, in fact, we can take limits and create isomonodromic deformations of connections which have irregular singularities. So in this sense, I speak about confluence. What I'm thinking about is that we go from a simple divisor of simple poles, we merge poles to create higher order singularities for our connection, and then reverse Reshetikhin's procedure and quantize to obtain a confluent version of KZ. So let me start a little bit with the setup. Well, and actually, first I would like to give you a little bit of a history of this topic. And perhaps I should say that the history I'm presenting here is more or less subjective in the sense that, of course, I will be forgetting a lot of papers every time I do this, and somebody I know is in the well, I mean, there are a number of people who get annoyed with me when I try to give a history. So I will not give a history, it's a subjective history. It's the history as I perceive it and as I understand it, okay? Which doesn't mean it's the real history. Okay, so anyway, so let me first of all say that isomonodromic deformation, sorry, I should have made a little bit of a parenthesis. Isomonodromic deformations are non-autonomous systems, Hamiltonian systems. And you can autonomize them with a very standard procedure. And when you do so, in the case of simple poles, they give rise to what is called Godin system. So the Godin system is kind of autonomous version. So what I'm trying to do now is to explain what is known about Godin system, quantization of Godin system, deformation of Godin system into non-autonomous system in the various situations to understand what is the state of the art of what we know about the form of these connections. So in the Reshetikhin result I was mentioning before, all poles are supposed to be simple. Regarding the Godin system, and its quantization, so the first results about quantization of the Godin system, maybe there was a paper by Mukhin, Tarasov, and Barchenko, and then, in fact, more recently by Talalaev, in which they defined these quantum Hamiltonians for the quantum Godin system as some elements in a large abelian subalgebra in the tensor product of the universal enveloping algebra. Then there are some papers by there is a paper by Frankel, Fagan, Frankel, and Rybnikov, in which they try to increase the order of poles. So they managed to introduce one irregular singularity so a pole of order 2 only. Then there is a paper by Fagan, Frankel, Toledano, Redo, in which they study again non-highest weight representations of the Godin algebra to try and construct some confluent Godin systems. So maybe this I can say it's confluent Godin. And then there is a paper by Vicedo and Yang in which they unify these last two approaches through some generalization of Varchenkov duality. So this is regarding the quantization of Godin, but this is still still autonomous system. Now, when you want to deform this system in such a way to make it non-autonomous, so by here means deform in the sense of making it non-autonomous, then there are some results by De Concini and Procesi. This is for AN root system, and still only one irregular singular point, and this irregular singular point still only of order 2. And also the work of Mielson, Toledano, and Laredo, which extended the De Concini-Procesi construction to the case of any complex Lie algebra. And finally, regarding KZ with any number of irregular singularities, there is a paper by Felder, Markov, Tarasov, and Varchenko in which they introduce the so-called dynamical KZ. This again has only one singularity, which is not a simple pole of order 2. Then there is the paper of Jimmo, Nagoya, and Sun, which is only in the case of SL2C, but in fact here finally we see any order of poles. And then there is also a recent result by Rembado, who generalized a result by Bolch, in which again we only have one irregular singularity of order 2, but for any simply laced linking diagram. So it appears that, dealing with many singularities and allowing any order of these poles has never been done, and that maybe the closest result is the one by Fagan, Frankel, Toledano, Laredo, but they never actually managed to deform the Godin system to obtain a non-autonomous system. So that's what I'm going to present today. By the way, if you want to ask me questions, please interrupt me. I don't look at the chat because I find it distracting. So if you want to ask me a question, please just barge in, or ask somebody through the chat to barge in for you. Okay, and I'm happy to take any questions you may have. All right, so anyway, this was just a historical little bit of an understanding of the topic, and let me give you the main ingredients. And I'm going to do something very simple. So I hope, even if you haven't understood any of the words I said before, I hope at least I convinced you that this topic may be interesting. And let me so present the, how to say, the frame, the setup in which we work. It's a very simple setup. We take the direct sum of many copies of the cotangent bundle of the easiest object in the world, which is the Lie algebra GLN. Okay, and on the copies, we can put a symplectic form, which is the easiest possible one, namely on every T star. So on every T star, if I express the local coordinates as PQ, I will take the form dpdq. Okay, so this is the super easy stuff that we don't need to even think to do. And then I call this object, for some reason, I will call it a universal phase space. So this is going to be the space where we work mostly. And I will show you that it contains, well, you know already that this is like one of very, very beautiful mathematical structure, but in particular, what I want to show you is that when you want to deal with differential equations and isomonodromic deformations of them, you can see them all in the same space in some sense. So I will start with some examples and then hopefully convince you. So on this space, what I can do is I can take, oops, what have I done? Oh, it's everything okay there? Yeah, oh, suddenly the screen disappeared from my iPad. So, okay. So I can take, so I'm taking D copies. D will be the degree of the divisor in P1 but for the moment, let's just take D to be an integer, okay? And then we act on this T star by D copies of the Lie group GLM. And again, we can think about this point in these D copies to be given by D elements, each of which in GLM. And then we can define some actions, which I can write explicitly in the local coordinates. So these two actions will be called inner action and outer action. And so, as I said before, in each copy, we can think about, in each copy of the cotangent bundle, we can put some coordinate P and Q. So let me now call them P1, Q1 for the first copy and P2, Q2 for the second, and so on. So I can act by this these D elements in GLM by acting separately on each copy. So I will act with G1 on the first copy, on G2 with the second copy, and so on until I act with GD on the very last copy. And the way, the way I act is in the inner case is to map QD to QD multiplied on the left by the inverse, multiplied on the right by the inverse of G, and P will be mapped by multiplied on the left. So that's why I call this action inner, because the G is inside, okay? And the outer action, instead, we do it the other way around. So we act with the inverse of the group element on the left of Q1 with the inverse, and on P, we act on the right. Okay, so two different actions. It's very simple and natural action to have on your cotangent bundle. Okay. So the point is that both of these actions are Hamiltonians. And therefore, we can look at the moment maps of these two actions. And the moment maps are commuting and equivariant. So I've written the two moment maps here. So the first one for the inner action, I will denote by mu I. And it will map my element to now the D copies of the Lie coalgebra of GLM. And so I will map, say, let me maybe take a red. So I map Q1, P1 to the product of Q1, P1, and Q2, P2 to the product of Q2, P2, and so on. This is the inner action. And the outer action is the other way around. So I will map the couple Q1, P1 into the product P1 times Q1, so in the other way. Okay, so these are two moment maps of my two actions. And as I said, they commute. So I can use the inner action to fix Qi Pi equal to something, say lambda I, for example, diagonal if that's possible, or Jordan normal form if it's not. And then act with the outer action. And because of the commutativity, what we have is that actually Pi Qi, the product the other way, belongs to, sorry, not to lambda, but to the coadjoint orbit of lambda. Okay, so that's very nice. We have essentially that we can use the product of these two quantities on one side to define the Jordan form, and on the other side to define a matrix whose Jordan form is lambda. Okay, So, well, okay, this is, I haven't done really nothing, anything interesting, but the point of this exercise is then you can prove that by doing a reduction of what I call the universal phase space, namely our D copies of the cotangent bundle by this inner action of GLM, we can obtain a map. So by doing this reduction, we obtain a map to the product of D coadjoint orbits. And this map is in fact a rational symplectomorphism. Okay. So I think, are there any questions so far? Hello? Nobody questions?
No, I don't think so. There's nobody there.
Okay.
People in the room, none of them waving a hand. I think we're all right.
Okay, cool. Right. Okay. I'm insisting on this. I mean, it's a fancy way to describe things because, you know, we are used to treat and work with products of coadjoint orbits, and we know how nice they are and so on. But I had an interest to express this as the image of such a reduction because I want to show you something a little bit more interesting very soon. But before I do so, let me first tell you that this product of coadjoint orbits is in fact the space on which we normally study isomonodromic deformations. In fact, if you look at, for example, Hitchin and also Michel Oden, they wrote two beautiful papers in the same volume of the NATO lecture notes. The idea is that when you want to study the isomonodromic deformations of a connection on some principal G bundle, the most natural space to do so is the product of coadjoint orbits when the connection has simple poles. And when you do so, the kind of isomonodromic deformations you have will be isomonodromic deformations of linear systems in which your matrix A will have simple poles, in particular D simple poles. Okay, and roughly speaking, what I have done so far is just to show you the mechanism by which we have this, and I simply, said this is because I've decided to act with these D copies of G in such a way that the first copy acts on the first copy of the T star and the second copy acts on the second copy. So I would like now to show you what happens when you start mixing things up, which is much more interesting. So now I would like to instead I take the same object as before. So again, I'm taking my universal phase space, which is still the same object as before. So D copies of the cotangent bundle. But now I want to act by mixing two of the copies of this T star GLM. Okay, so I'm still taking a bunch of G's. For the moment, let me a bit sloppy. Okay, GD. Let me say that G1 belongs to GLM. The others actually we can take in the Lie algebra, but let me be a bit sloppy. So what I'm doing, I will act with the G1 and G2 by mixing on the first two copies of the this cotangent bundle, and then everybody else is acting on a single copy like before. And so I'm going to write here this mysterious action. Okay. I will give you in a second how we found this action. Of course, it's not black magic. There is a formula for it. But as you see, what I'm doing is I'm mixing. Q1 now doesn't only go to Q1 times G1 to the -1, but there is also a term which depends on Q2 and carries some multiplication of G2 by G1 minus 1 and G1 minus 1 again. So it's a kind of a mixing action. And the point is that this action is again a Hamiltonian action of which you can define a moment map and for which you can carry out a reduction in such a way that it's a symplectomorphism. It's just that now, instead of having the product of the coadjoint orbit, standard coadjoint orbit, you have a new coadjoint orbit which carries a little hat. And this is a coadjoint orbit of another, not GLM, but a truncated loop algebra associated to GLM. So now a little bit less mystery, let me perhaps say this. So what I'm doing really is to replace my GLM by loop algebra and then doing a truncation. Okay, so for example, in this case, I'm truncating all the currents to the second order. And then what I'm doing really is acting on this by the corresponding Lie group, which will also depend on the parameter Z. And in fact, these formulae are nothing else than the group element like before, multiplying now everything with series and polynomials. So this is no mystery, just to let me say, action of the Takif group. I will explain this maybe later if I have questions. I just wanted to emphasize this is not kind of a miracle or a rabbit coming out of my hat. Okay, but what I wanted to point out is that we can start mixing. If before we kind of had this situation in which each element, G1, was acting on the first copy, G2 on the second copy, we can think of it in terms of Young tableaus, like a Young tableau with D boxes, and this is vertical. In this example I've given here, we will have that our Young tableau again has D boxes, but the first two are on the same line. Okay, and the point is that now we have reduced our universal phase space by changing the way in which the group acts. We have reduced it to a different product of coadjoint orbits, in which one of these coadjoint orbits is coadjoint orbit in a current algebra. And this also you can map to flat connections on a principal bundle of the Riemann sphere, but now your divisor is no longer made of simple poles, it has a double pole. Okay, so this I express by saying instead of having D singularities, we have D minus 1, but one of them has order 2. Okay, and we could keep going. So I could now start acting on 3, on 4, all the same mixing and so on. And so here I've made a little bit of a drawing about the case when you have degree 4. So in the case we can have 4 simple poles, or 1 double pole and 2 simple poles, or 2 double poles, or 1 triple pole and simple pole, or a quadruple pole. And in all these cases we can give such description. If you then decide that instead of GLM you restrict to SL2, then you get the Jimbo-Soon construction, which is kind of which I will talk about later, which brings down to the Pandré equations. Ramified, which means that some cases of those equations are not done. For the ramified case, there is some work in progress. By my student, Ilya. And it has actually very interesting aspects, which I think have a lot to do with the Springer resolution, but never mind, not the topic of today's talk. Okay, right, next. So let me give you now the general setup for this work. So the general setup is we start by considering two integers, okay, in which one is smaller than the other, in particular n is smaller than d. And then we choose some other integers, positive integers, r1 to rn plus 1, such that the sum of all the ri's plus n plus 1 is equal to d. Okay. So this is the d is the degree essentially of my divisor. Made of n plus 1 points, each of multiplicity ri plus 1, okay? And so we can arrange all this data in many different ways using Young tableaus. What I want all Young tableaus which have n plus 1 rows, and each column has ri plus 1 boxes. And according to the arrangement I choose, we can select a group action which will send our universal phase space. Oops. By some group action, we'll send it to the product of some coadjoint orbits, and these are going to be coadjoint orbits in the truncated loop algebra, in which we have truncated at order r plus 1. Okay, and the point is that on this space, this is where we study isomonodromic deformations for connections which have n plus 1 singularities, and each of order ri plus 1. And yes, so this is the natural space to study isomonodromic deformations. This space, the product of coadjoint orbits, is very nice. So it has a Poisson structure. This is the standard Poisson structure Constant-Kirillov construction, if you want, that you can put on the product of coadjoint orbits. And I briefly described this structure here. So what this Poisson structure does is that elements belonging to different coadjoint orbits Poisson commute, and within each Poisson or each coadjoint orbit, I can think about elements to be given by Laurent polynomials of order r plus 1, and the coefficients of these Laurent polynomials have non-zero Poisson bracket only when the indices sum up to the maximum r. This is essentially the truncation. What's going on here is, because I'm truncating everything at r, essentially what I'm saying is that if I commute two objects, say I commute a k z to the p, sorry, a k z to the k plus 1, and I want to see with zl plus 1, if 2 plus k plus l is bigger than r plus 1, oops, then I have to throw it away because I have a truncation to do, okay? And that's why we have 0 here. Otherwise, we have standard Poisson bracket that can be expressed in this commutator way, where pi is just a standard permutation matrix in okay, so the cute thing here is that essentially with this structure we can reproduce the theorem that the reduction with respect to whatever group action we take according to the data we have chosen, so to the Young tableau we have chosen, the reduction to the prototype adjoint orbits is a symplectomorphism, which means in particular that what we do, we map the Darboux coordinates. So we have this the PDQ symplectic form. This will go to the Poisson bracket, the natural Poisson bracket, and namely the natural symplectic structure induced by this natural Poisson bracket on the symplectic leaves given by the products of conjoint orbits. Okay. Are there any questions so far? No. All right. Well, okay. So now I would like to start.
Excuse me, please.
Mm-hmm.
Please, sorry for taking you back. The Young tableau that you described, that ordering, which you talk, it has to do with Springer resolution. So
no, the ramified case.
yeah, this ramified case.
Yeah.
So do they index a nipotent orbit?
Yes.
Okay.
So ramified exactly means that that you have nipotent orbits. Yes.
All right.
Yeah. But that's not my work. Is Ilya Gayur is doing this work, and hopefully it will be in his thesis, which hopefully should be ready soon. Okay. So, okay, where was I? I wanted to do isomonodromic deformations. So let's go back to the case when we have only regular singular points. So this was the simple case in which we simply have a divisor of simple poles. So we consider linear systems of differential equations. And let me write the differential equation system. D over d lambda y equal to, okay? What we want to do is to take this system and deform it in such a way that the monodromy data, or if you are more happy to discuss connections, the holonomy of the connection is constant along the deformations. And the point is that when you do deformations, you need to decide what are your independent variables and what are your dependent variables. So the natural independent variables in the deformation are the position of the poles, because as long as we take all our simple poles in such a way that they remain simple, so if I take them as elements of the configuration space of D points, then that's a very good choice of my linearly of my independent variables. And then I deform, so I impose that the holonomy is constant, and what we find is that these matrices A will become functions of the position of the poles. And that's the standard case, which is well understood. What happens in the irregular case, now we have a much more complicated situation, because here we have less poles, okay? We have only N. I remind you that N is smaller than D. And some of them, so in each of these orbits, I've got contributions. So for example, here I will have say A1 for the first orbit. I will have, okay, I'm sorry for the awful notation, but I will have maybe this, but then I have all the other contributions for the pole which is of higher order, and so on, okay? So what we find is that, unfortunately, the position of the poles are not enough to deform this system because we are losing, we have only n poles, so we are losing d minus n of them, okay? So the problem here is to study isomonodromic deformations which are general and the intuition doesn't help. So what we do is to introduce some extra times by essentially studying the continuous linear Poisson morphisms of these Ta'Keefe algebras. So the point is that we want to introduce some extra, so let me write it here, maybe need extra deformation parameters. And to find these, we use a parameterization of all the possible continuous linear Poisson morphisms of our Ta'Keefe algebra. Namely, what we do is that we assume, for example, to have a pole of order r plus 1, and we ask ourselves, suppose we have another matrix with a pole of order r plus 1. Do they satisfy the same Poisson brackets or not? And the reason is, the answer is yes, they do, as long as they are related, these two matrices, by a transformation which is very simple, and in which we can explicitly actually compute this matrix T. And what we find is that essentially each pole of order R will bring extra deformation parameters T1 to TR, okay, in a very explicit fashion. So, so for example, if I want to consider the generic system which has a pole of order 4 at 0, I will have that I can define a 3-parameter family of which then I can move T1, T2, and T3 as independent variable to make my isomonodromic deformations. And the crucial point is that then we can, in fact, compute all the Hamiltonians of these isomonodromic deformations. Why do I care? Well, because to quantize, I would like to remind the ultimate aim of this talk was to introduce some quantum system. So when you want to introduce some quantum differential equation, well, the easiest way to do it is to consider a classical equation in Hamiltonian form and just quantize in Heisenberg way. So the reason why we care about having the Hamiltonians explicitly is because we want to quantize. So what we can prove is that the Hamiltonians are very explicit. So what you do, you have your system, linear system that you want to deform. Then you compute the spectral invariants of this system, which are simple, if you want, residues of some z to the k trace of a square. These are the so-called Godin Hamiltonians. But then you construct the non-autonomous Hamiltonians by a simple operation which involves inverting the same matrix that I found before. So this matrix is kind of key into the process. So somehow the class, the Poisson morphism class of these products of cojoint orbits is fundamental, both to tell you how to start the isomonodromic deformations, but also how to compute the Hamiltonians. Okay. So to prove these results, I will maybe only give you some ideas. The reason why I'm giving you the idea is because it also explains in what sense we talk about confluence. So the basic idea is that, as I said, the theory, in the case when we have systems with simple poles, everything is understood. We know how to deform them. We know how to write the Hamiltonians. We know the quantization. It's the standard KZ that Reshetikhin studied. So we know everything in this case. And what we do is we start performing some rather tedious asymptotics in which we coalesce two of the simple poles together along some direction. Okay, so suppose I put two of the poles together, but you know, we are on the complex Riemann sphere, so there's several ways that I can do that. And so I want to keep track of the way in which I do this by defining a T1. When I do this and I take the limit as epsilon goes to 0, I produce a new system, which is this guy, in which I still have, you know, the first part of the system has remained the same. But the second part of the system, these two poles have merged to create an order 2 pole. And the information of the way in which I've coalesced these 2 points remains explicitly in the confluent system. So these are called confluent. Then I can repeat this process again. I now want to coalesce another point with this. So I again do a change of variable and take the limit as epsilon goes to 0, and so on and so forth. Oops, sorry, maybe, oh, I don't know what I've done in my eye, but okay. Can you see? Okay, yes. All right, so by doing this procedure, what we can do is to confluence the theory as well. So what we can do is to understand how to confluence the Poisson structure in this case, and the Hamiltonian description and everything, and confluence it to the next case and then to the next case. And that's how we prove the results. All right, so in this sense, we talk about confluence, but the nice thing about it is that despite the process being rather analytical, there are very good algebraic reasons why these T's appear in the way they are. As I explained before, it's because of the class of Poisson morphisms in the Takif algebra. All right. So now I have a little bit of time, so I would like to discuss the quantization. So the quantization is actually pretty simple in the sense that really we more or less do the same as we did classically. So what we have is that the quantum Hamiltonians now will be elements in the tensor product of universal enveloping algebras, of these Takif algebras, and the explicit formulae for them are the same as the classical ones, in which we replace everything by the quantum analog, okay? And here, I have the quantum residue of an object which has a square, but it's not a problem because there is no quantum ordering problem, because these objects that I had before, they are now the quantum Godin. So they're well defined and actually Poisson commute, quantum commute, because they are the elements of the quantum Godin algebra. You could also prove by brute force commutativity. It's a little bit exasperating, but it actually works, so it's not a big deal. The nice thing is that then, given these Hamiltonians, you can define some operators which do define a quantum integrable system in the sense that they quantum commute. So this quantum integrable system is what we call confluent casing. Okay. So, so maybe let me go back to 1 second to this point. As I said, there is a B square there. So one way you can decide to choose your quantum order is really lexicographical. So you decide that in taking that B square, remember B is now an element in the Takif algebra, so it's a Laurent polynomial. And so when I take trace of B square, I will have products of different terms in B. And so I will keep on the left the one which are on the left in the matrix product. And so the lexicographical ordering is one of the orderings that works in a consistent way. And you can, as I said, you can prove that by brute force if you really want to spend a few days computing. All right. So the other thing I wanted to discuss very briefly is the relation between this object and the so-called semi-classical solutions. So semi-classical solutions are solutions of this system, of this confluence KZ, which are very interesting. So let me, roughly speaking, this is stuff that comes in physics. They are objects that go like exponential of I over h bar of the action function. And the statement in Reshetikhin paper, at least for the simple pose, he wrote something along the line that these semi-classical solutions are in fact tau functions of the isomonodromic deformations. Tau functions is an object which is related to the Hamiltonian. Okay, so D, it's D log tau is H dt. Okay, if you, this is what the tau function is. And this statement by Reshetikhin is actually without any proof in the paper. So now we actually understand it. And it's essentially the fact that because of the presence of the action functional and the fact that Hamiltonians are all quadratic in A, you remember that we had the Hamiltonians are some linear combinations. Where did I write them? Here. Are some linear combinations of these objects which are quadratic in B. And let me remind you that these B's are quadratic. Each B is a product of P and Q's, okay? So the Hamiltonians are homogeneous of degree 2 in P. And therefore, when you compute the action, you find exactly the tau function. And that's why even for the confluent KZ equations, the semi-classical solutions correspond to the tau functions. So I think I finished. And if anybody wants to ask any questions, I'll be happy to answer.
Thank you.
Thanks.
Alan, are there any questions in the chat?
Oh, let me see.
Alan's been monitoring the chat, so.
Okay, thank you.
Are there any questions from anybody in the room? Doesn't seem so.
No, okay, I managed.
But just to reassure you, Marta, there are 20-something people in this room who have been listening to you. So
No, it's okay.
you've not just been talking to the wall, which happened to me once, but I dropped the connection and talked to the wall for 20 minutes before anybody could tell me. That was in the early days before we really got used to things. Anyway, thank you very much. It was a very nice talk.
My pleasure.
And the next talk, well, so Marta's ended a few minutes early, so the next talk is at 5? Yes.
Okay, I'll go
Thank
for
you.
coffee then. Thank you.